This is looks like okay. Okay, look at this. Is that a heating or cooling curve?
A cooling curve.
It's a cooling curve. Oh, it's done. It says here, okay, cooling curve. The experiment is done determining the cooling curve of water. After completion of the experiment, the following graph is drawn. At line HI, condensation of water vapor occurs. At the JK, ice forms. So let's fill in. We're not going to even answer all those questions. We're just going to fill in the values. So this is like a solid here. So this is a liquid. And this is gas. No, I'm lying. This is a solid here. This is this is when the water vapor is a vapor form or a gas. So it's gas. Then these two areas here, which is yellow, is the areas where transition between a gas and a liquid takes place. And between J and K, there's a transition between a liquid and a solid. What is indicated by the y-axis? Anyone?
Your
Obviously, the x-axis is time.
okay.
Temperature.
So your y-axis would be your temperature.
Yeah. What is indicated by the x-axis? Time.
Your
The time.
okay.
Good. Okay, I've got another scan here. Numbers. Okay, good. What happens with the potential? I'm struggling to speak to you if you move around like that the whole time. There's something on the mic or something that's not right.
No.
What happens with the potential energy and kinetic energy at Ji and Jk? What happens with the kinetic energy?
When the particles become a liquid and a gas, the kinetic energy increases.
No, they're asking what happens with the potential and kinetic energy at Ji, which is that one yellow section, and Jk, the other yellow section. The kinetic energy stays the same. Okay. In the green sections, the kinetic energy changes. The kinetic energy decreases. As remember, the molecules moves really quickly and loose from one another in a gas. And once it becomes a liquid, it comes closer to one another. So the movement is less. So the kinetic energy is less. Kinetic energy is directly proportional to the speed of the molecule. The potential energy increases. We did this. Good. There's another page somewhere.
Sir, I sent you all the pages.
Okay. Right. I'm not sure about the order. I've got the last page sent second. What is the next page?
Which page, sir?
I'm looking for the next page. Was this the first page? I've got another scan here.
This is the 7th page.
Was this the 7th page?
Yeah.
Okay, I've got the
The
first
page
page
number
now.
is at the bottom.
Yeah, the page number's at the bottom.
Okay. Do you have the experiment in front of you?
Yes, sir.
Yes, sir.
Do you mind if we do it in a different we don't do the first page first, because I can't find the second page, to be honest.
Yeah, okay.
Okay, I'll just do the next page sent to me. Right. Explain the 3 lines on your graph. Oh, is this the next page? Oh. Sorry. You'll have to send it to me in another way. I don't know what the second page is because the numbers are cut off by the photos. I can't see the page numbers. Or you can tell me what the next page looks like.
Okay.
Okay, this was sent in the correct. Makes it difficult, eh? What you should have done for today, you should have gone through the experiment and asked questions. This is what you should have done. This is a right way of doing the class. So you should have done, gone through all the pages and then ask questions. So this is the first page, isn't it?
Yes. Yes,
Okay.
sir.
So you have to do this, physically do this. Fill a heat-resistant glass beaker with ice, place a thermometer in the beaker. Do you have all this stuff? And measure the temperature every 2 minutes while the ice is melting. Heat it with a Bunsen burner or on a stove. Place a thermometer in the beaker, blah, blah, blah. Did you actually do this?
No.
We do not have exactly all the equipment.
The ice absorbs heat until the ice is melted. Okay, you don't have all the equipment, so that's a big problem.
Yeah.
Okay. This is a big problem, people, because you won't have values then that you're going to fill into your graph. So we're going to spend this whole lesson trying to figure this out.
Okay.
Are you happy with that?
Yeah. Yeah.
Okay, what is the aim of the experiment?
We need to determine the boiling point of water.
Determine, I think we're going to do melting point, because we're starting with a solid, isn't it? So what is the melting point? Or do you know melting point of water? And what is the term we use when something is a gas and becomes oh no, you're starting the experiment with ice, isn't it?
Yes.
Okay, so it is what? Melting point and boiling point, isn't it?
Yes, sir.
Yes.
Melting point and the boiling point of water. Very good. Okay, try write investigative question for this experiment. I can't help you with this. You must each have your own investigative question.
Okay.
Identify the variables. Okay, what is dependent and what is independent? What is controlled variables?
So is independent variables one that you cannot control, that happens by itself?
Yeah, the dependent variable is normally on the y-axis and the independent is on the x-axis. So the independent variable is something that you regulate. Oh, sorry, the dependent variable is what happens after you're doing something. So what is dependent?
It happens with your intent.
Yeah. So what's that? Temperature.
So, yeah.
I would say the dependent variable is either temperature. I don't know actually, to be honest, what you're going to do here. The independent variable is which change. This is time, isn't it? Time changes, or is the temperature changing? Which one are you going to use as independent? And controlled. What is a controlled variable? That which remains the same. We'll have to come back to this because I'm not sure what you're going to do with this experiment. So fill a heat-resistant glass beaker, place a thermometer in the beaker and measure the temperature every 2 minutes while the ice is melting. Heat it with a Bunsen burner or stove, blah, blah, blah. Place a thermometer in the beaker and keep on heating until the temperature is more or less 100 degrees. Use a stopwatch to measure the time and take the reading of the thermometer every 2 minutes. Do not keep the thermometer in one position as only measures temperature. Okay, you must stir the thermometer. Keep on making readings until the water boils. So what changes the whole time? Which is changed? Okay, we're going to make a question here because not sure. The dependent variable is the thing that you measure, and you measure the temperature of the water. Is that correct? Speak to me, Calvin. I can't hear you.
Sorry, sir. It was mute.
In your book, you'll have the same experiment. And that will give you an idea of what is used as the dependent variable and the independent variable. We can come back to this.
Okay.
Okay, this is, you can do this, a glass beaker, and show a photo of the apparatus used. I would say the controlled variable is the time intervals. That stays the same. And which is changing? Phase. But we'll come back to that. Next question. Just want to make sure we know exactly what's happening with this experiment. Now I have to find the next page. I'm struggling to find the next page. Okay. You'll have to do this experiment. Look at the next page. You have to physically do the experiment. Look at this. How are you going to fake this if you're not doing the experiment? Okay, which measures of safety are you going to use?
You need to be sure not to burn. So you just always gloves.
So burn, you're going to wear gloves. 2, please. You're going to work with, if you work with an open flame, you're going to remove flammables, remove stuff that can burn. Stuff like that. Okay, think of another one. Yes, I've already given the instruction. What is your observation? Yes, you must write in exactly what you see. As the temperature increases, what?
The ice will melt.
Yeah. As the time on the stove increases, so the temperature increases. The longer you keep it on the stove, the higher the temperature goes. Other observation is that your ice starts melting, and once it starts melting, it doesn't immediately go into solid. All the blocks of ice first melt, and then it becomes a liquid. Okay, this is a problem you have. You don't have temperature readings here. Every 2 minutes, you need to take a temperature reading.
Oh my God.
You see that this is a problem if you don't do the experiment. If you don't have a thermometer, you have a problem. Okay.
Okay.
Right. So we are going to have a small problem here. At least you know that the temperature after 2 minutes is not going to be 0, because right at the beginning, the temperature was 0.
Okay.
So we have a problem here. Okay. Because this they're going to know that you cheated. If you just add 1 every minute, 1 degree every minute, they know you cheat. So this is a big problem. You should have done this earlier.
So what we'll do is I can ask Krista and some of the teachers by the centers, they have some of the equipment and maybe we can do this, the measuring of the temperatures here at the same time.
Yeah, you'll have to find somewhere how to do it. Look, it's just a thermometer really that you need, because getting a stove or something is not that difficult.
Okay.
Where is this now? Okay, this is a graph. This is another problem you have. You'll have to take this graph, to draw a graph of temperature versus time on your values. Make sure that all headings and labels of units are given the best fit line. So what they're going to do, they're going to give you this graph paper, and then you're going to do the time on the x-axis. And you're going to do the temperature in degrees Celsius. So your temperature in degrees Celsius, you're going to do on the x-axis, on the y-axis. And you're going to, every 2 minutes, it's probably going to be one of those lines every 2 minutes. So you're going to make a dot there, and you're going to make a best fitting line. That's another problem that you have, because you have to have all those values to put into the graph. You can't just draw a graph. Do you understand?
Yes.
So if you go back to this table, then every 2 minutes is going to be a line on the graph up till 68 minutes. And then you'll have to make a dot at the temperature reading. Do you understand what to do?
Yes.
Yes, sir.
You're going to get to 68 minutes here somewhere at the end. And you'll have to make a dot, and then you try and fit the line. Your line's obviously going to be something like this, eh? Do you know that?
Okay.
Because this is when it's a solid, then this is a transition time, this is when it's a liquid transition, and this is where it's a gas. You'll probably have the thing is, this is going to be very difficult to get it a gas, because it's going to boil off. So do they specify how much liquid you have to use?
I don't think so.
No.
No,
Don't-
they don't.
Don't take a huge block of ice, eh? Don't take a big, like a 4-liter container of ice. Just make a small one. Okay, just like a cup.
Okay.
Otherwise, it's gonna take too long to boil. You're never gonna get it to a gas. Okay, next page. Okay, you're starting to understand what I'm expecting of you.
Yes.
I was expecting you today to complete this and then ask me questions. Then explain the 3 lines on your graph in terms of potential and kinetic energy. Okay, right. This is important, because this I can help you with without any readings. So your graph is going to look something like this. It's going to start off, have a line like that, go like that, up, horizontal, and vertical. So these areas that are green is where your temperature increases. So the first section will be a solid. So it'll be a solid ice, or just ice, and then it will transition. There will be a transition area into a liquid form, which is water, and then it will be a gas. So in those green areas, which is vertical lines, isn't it? The yellow ones are horizontal. In the horizontal line, the potential energy increases and the kinetic energy stays the same. So in each one of these yellow lines, the kinetic energy remains the same, remains constant. While the potential energy potential, EP is energy potential, increases. First horizontal, explain the 3 lines on your graph in terms of potential energy and kinetic energy change. In the first horizontal line, the potential energy increases, but the kinetic energy remains the same. Between the horizontal lines, we have got those green lines. So in the green lines, all the green lines, doesn't matter which they are, the kinetic energy increases and the potential energy remains the same, remains constant. Second horizontal line. Well, it's the same. Conclusion. Okay. This you can write now. In the horizontal lines, the kinetic energy remains constant and the potential energy increases. And in the vertical lines, or between the horizontal lines, the kinetic energy increases and potential energy remains the same. I'm not sure how they thought you would know this. Evaluation. Okay, I don't know what that means. What does it mean, evaluate? Evaluate what? Huh? What do they want you to evaluate? Yeah, I don't understand why the value, evaluate what?
Um,
Okay, now you've got this thing. It's not difficult. I mean, the next question is the first one we did. And that's your second last page. And this is basically the same question. So this is a cooling curve. What is indicated by the y-axis? Temperature in degrees, yeah, temperature in degrees Celsius. What is indicated by the x-axis? Well, time in, I don't know, minutes or seconds. It doesn't matter. We don't know.
yeah.
What happens with the potential and kinetic energy at Ji and Jk? Okay, that you know already. In these horizontal lines, the kinetic energy remains the same and the potential energy will decrease, eh? Important. Potential energy will decrease here. Why?
Because it is, yeah.
The cooling curve. And also important, in those purple lines, the kinetic energy will decrease. It will go slower, the molecules. I wonder why they didn't ask that. It's kind of more important. Oh, they are asking that in the next one. This is the last page. So I'm just going to copy that graph again. What's that noise? Okay. What happens with the potential kinetic energy at Ij? There. The kinetic energy decreases and the potential energy remains constant. Do you have that? I mean, all of the questions are the same. What is represented by A on the graph? Anyone help me? A. A is where it moves from a gas to a liquid, but it's also the temperature at which a liquid becomes a gas. So that's basically its boiling point, isn't it?
Yes.
It's when the gas becomes a liquid, or it's at that temperature where the liquid becomes a gas. So it's boiling point. Give the value. Oh, awesome. I wouldn't know. Is this water?
Yes.
Okay, if it's water, it's 100 degrees Celsius. What is represented by B on the graph? Melting point. Huh. Are you with me?
Yes, sir.
And what's that? 0 degrees Celsius if it's water. Why is the boiling point of water not always 100 degrees Celsius at every place on Earth? Give a reason for your answer. It's got to do with the definition of boiling point. What is the definition of boiling point? The definition of boiling point is extremely important. It's when the vapor pressure is equal to the atmospheric pressure. So why is the boiling point on Mount Everest? If you climb up Mount Everest, you make a coffee there, you can boil water at 76 degrees Celsius. 67, yeah, 67 or 76. Why? Because the atmospheric pressure is much lower. So it's only 100 degrees Celsius at what? 1 atmospheric pressure. In other words, sea level.
Okay.
You stay where? In Gauteng?
Yes.
Yes.
The temperature of boiling water is slightly under 100 degrees Celsius in Gauteng. I'm in Cape Town, so it's 100 degrees here. I'm on sea level. So, okay, only one, the boiling point of water is only 100 degrees Celsius at 1 atmosphere pressure or sea level. If you go higher, if your atmospheric pressure is higher, is lower, so you went up higher, you're on a mountain, water will boil at a lower temperature. So let me explain it this way. There's your beaker of water in it. There's water in it. I'm going to make it blue. So the water molecules wants to come out of the beaker, but there's something pushing it down. There's a force on top of the surface of the water pushing the molecules down, and that's called atmospheric pressure. The higher that pressure, the more difficult it becomes to boil. So if we lower the atmospheric pressure, then the water molecules, the water vapor will just come off. So you can make water boil without adding any temperature to it. You can just lower the pressure. How will the boiling point of water differ when a person climbs a mountain such as Kilimanjaro? Boiling point will be what? Be lower.
Less.
Okay, give a reason. Well, the reason is in the previous one. The atmospheric pressure on the mountain is lower. Therefore, the water will boil at a lower pressure. Because it's higher, because the elevation is higher than sea level. Yeah? The pressure will be lower and therefore it will boil at a lower temperature. You've got that, Calvin. Do you understand that?
Yes, sir.
Okay, so I don't need to write that down. Okay. All right, let's get back to, you'll have to do this before you can answer. I'm just not sure about this one. The problem I've got with this question is the following. The dependent variable is normally the y-axis. Independent is the x-axis. So in our experiment, the x-axis is time and the y-axis is what? Temperature. It does make sense because which is measured? What do we measure? We measure the temperature. What changes all the time? Well, the time changes. It's kind of unfair because we're also forcing the time in a sense to change. What is the controlled variable?
The temperature.
No. I would say the liquid that you use.
Okay.
I would say that is a possible control. Why? Because we're using the same liquid. We're having just water. That's control. Or the purity of the water. That's what we control. That's which remains the same. That doesn't change. The minute you put something else in the beaker, all your readings going to be changed. So we make sure that we're using water, the liquid used, or the substance used, the purity of it. But I might be wrong on this. The first two is correct, but the controlled variables kind of interesting. Okay, quickly scan through that and ask me more questions.
So I have a question at number 4. It says what happens with the potential and kinetic energy at
What page are you now?
page 8.
That one.
The top one. I just want to make sure I heard it correctly.
Okay,
Is it that
number 4, what happens with the potential and kinetic energy at IJ? That one.
Yes.
IJ is this liquid one. Yeah, isn't it?
Okay.
Okay, well, what is happening there? It's what? It's a liquid. It's that whole section there, the water is in the form of a liquid. We are cooling it. It's become cooler. Cooling means that the molecules are moving slower. So the kinetic energy, I'm just going to write E for, okay, let me write energy, is decreasing. What does that mean? What does that really mean? The molecules are moving slower as we're cooling it. Can you visualize the molecules? They're moving very quickly, and the cooler we make it, the slower they're going to move. So the kinetic energy is basically the speed of the molecules, directly proportional to the speed of the molecule. So the kinetic energy is decreasing, but the potential energy is constant. That doesn't change as it's in the same phase. It doesn't change. The potential energy changes on the blue parts, not on the purple parts. Potential energy remains constant. Back in a second. So where's that in your textbook? Do you have a page number in your textbook?
4.
Because I think all of this is in a textbook.
I'm quickly having a look.
I think all of this, I've got an old textbook here, and all of this, the cooling and heating curve is in the textbook with explaining each horizontal and vertical section in words. Do you have that?
No, we don't.
You don't have that. So they've changed the book, so you don't have any of those in there. So I just want to see if there's no exercise like that also in here. No. Okay, I understand. They've just taken that out.
So we found one.
We found one. So they explain all of that there.
Okay. It's more or less an exercise related question to this.
Pardon?
It's mostly like a question or bunch of questions, the same as this.
Yes.
Would you like us to send you a picture?
No, it's fine. As long as you've got it there, you can use it as a reference.
Okay.
Because the only one thing that we're not 100% sure of is what is the dependent and independent variable and controlled variable.
Yes.
Okay, there's not just one possible answer for controlled variable. There's more. There's more than one. I just want to check how many possible ones can they give. Okay. Just give me a second. There's actually, Okay, yeah. Are you familiar with I was wondering if it's those Siyavula books, it's got them in. They don't. I was wondering if you could get it online. There's an online free book that's got it in, but it doesn't have the same questions. I thought it's going to have heating and cooling curve thing. Okay, but if you struggle, you can always just WhatsApp me
Okay.
and I'll give you the ones. Okay, but you must go and see what you can get right on this and do the experiment.
Okay.
Right. Okay, let's go on. We've got 20 minutes. Let's just do something more. Okay, last week, we played around with protons and neutrons. Remember this? And electrons. Do you remember this?
Yes.
Okay, so all of this we did. Protons, electrons, and neutrons. Can you remember that?
Yes. Yes.
This is what we did. More models with protons, neutrons, and electrons. So I'm going to copy this one again. Just this one. I want to show you something new. Okay, this was chlorine. How did we know that this was chlorine? If we didn't have any of this, so for instance, this is deleted. So for instance, I delete this. How would you know that this Bohr diagram represents chlorine? Why? Because chlorine is the only atom that's got 17 protons. So let's make this 1735. So the amount of protons equals 17. And can anyone tell me the amount of neutrons? Come, Calvin. Neutrons. Look, 35 is his mass number. So 35 is composed of 17 protons plus, I don't know how many neutrons. Well, it must be 18. You see that?
Yes.
So the neutrons are 18. How many electrons do we have?
17.
17. Okay, excellent. Now,
So I wanted to ask, sorry, the charges on the polyatomic ions. Do we
yes,
need to study those
Yes.
charges along with the formula?
yeah, you need to study.
Okay.
Okay, but now what we're going to do something new. It's called Aufbau diagram. Aufbau diagram is just a visual representation of the electrons. So look at this. I'm just going to delete this section here. You're going to make a drawing of the energy fields in which the electrons are moving. So chlorine is in period number 3. Go look in your periodic table. It's in group 6, but the period is number 3. The periods are those horizontal groups. Can you see that?
Yes.
So there we have chlorine. It's in the third period. So chlorine will have 3 energy areas in which electrons will move. Now, the first area is called n equals 1. And that area only has a 1 orbital. It's called the s orbital. So we call it number 1s. That is an orbital, an area in which electrons will move. Then the second, okay, this is represented by this blue area there. So there's 2 electrons there. Then the next energy field is, I'm making it green. It's called n equals 2. So that's the second energy field. And that consists of an orbital. An orbital is just an area. It's called 2s. Okay? And 3 other areas called p orbitals, 2p. So s orbital is just a spheric orbital. It's electrons moving around. So if this is the nucleus, the s orbital is a round orbital in which electrons can move around the nucleus. A p orbital looks like this, like something like that. And there's 3 of them. And they can take each 2 electrons. And those electrons move in a figure 8 around the nucleus. So the second energy field, now the Bohr diagram, that's green line, only shows the circular thing, but that's the way it's represented. But it consists of one of those s orbitals and 3 of the p orbitals. And then we have a third energy field, n equals 3. That consists of a s orbital, it's called 3s, and it's consisting of 3 p orbitals called 3p. This you'll have to learn. We will spend more time on it next week because we're moving in that direction. So now I have to fit in all the electrons. Now in that blue part, right, the first circle around the nucleus, we have 2 electrons, 1, 2. And you are going to indicate it by half arrows pointing up and down. Then in the next energy field, there's a total of, if you can count that, 2, 4, 6, 8 electrons. Can you see in that green section, there's 8 electrons, 2, 4, 6, 8. There's 2 electrons in an s orbital. Then there's 1, 2, 3, 4, 5, 6 other electrons. The last energy field is going to be purple. Well, I'm not going to make it purple because I can't see anything then. So let's just make it yellow. That's also 8 electrons. In the s orbital, there's 2 electrons, and then in p orbitals, there'll be 1, 2, 3, 4, 5, 6. Is that 6? No, there's 1 missing. 1, 2, 3, 4, 5, 6. It's not 6, it's 5. So I've added 17 electrons to the chlorine Aufbau diagram. Have you seen this before?
No.
So what I want you to do, I want you to finish this task as soon as possible. It's got to be in tomorrow. You have to finish it today. I don't know how. And then I want you to study or read through your work up to Aufbau diagrams. And then next week, we'll quickly do your questions on Aufbau diagrams. And then we're going to move over to chemical bonding because we have to speed up. Okay? It's not that difficult. All you need to remember or learn, you don't know it now, you'll have to go and learn it. The first energy field only has 1 orbital. It's called a 1s orbital. It can only house 2 electrons. Every field or every energy area after that or field after that can take 8 electrons in total. Those 8 electrons will be placed in a s orbital, and the number in front is just the energy area, number 2, and it will be 3 p orbitals. The p orbitals can take 6 electrons, and the s orbital can take 2. The s is always filled first because it's closer to the nucleus. Is filled in second, and then the last. Okay, this doesn't have a full electron. There's only 2, 4, 6, 7 at the end, and those 7 goes in like that. There's 1 missing. Let's do 1 more. Let's do 1 more. Right. So I'm just going to say nitrogen. Nitrogen is number 7 on your periodic table. Let's just draw an Aufbau diagram. Okay, so it's got 7 electrons. Is that correct?
Yes.
So the first energy field number 1, only has 1 orbital. It's called a 1s. Energy field number 2, oops, not number 0. Number 2, it's got an s orbital. It's called 2s. And 3 p orbitals. Okay, I only have to draw 2 because nitrogen is in period 2. It's not wrong to draw the third one. It's not wrong, but I'm not going to use it. I'm going to put my 7 electrons in. The first 2 goes here, 1, 2. Then the next 2, number 3, number 4 goes in there. And then I fill the p orbitals 1 at a time. So electron number 5, number 6, number 7. I'm not allowed to group them before I fill the others. Why? Because electrons are negative and they actually repel one another. So you always fill in 1 electron in each orbital. And if there's any other electron, then I just start with the first one again. So look at the difference between nitrogen and what? Oxygen. Oxygen is number 8. So we have 8 electrons. So this Aufbau diagram is going to look exactly the same. But I'm just going to add 8 electrons. So let's just fill those last orbitals again. There's 3 orbitals. So I've got 4 electrons, 5, 6, 7, and then that one is 8. So there's oxygen with its 8 electrons. Okay, try and do the following one. On your own, go to the periodic table and fill in sulfur. Go and look in what period it is. It's period 3. So you're going to have 3 energy fields. Quickly make a drawing of that. That. See if you can fill in. Get sulfur's atomic number and fill in. And I have to show you one thing and then we're finished. Right, help me. Sulfur is what? Number 16.
Yes.
So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That cool?
Yes.
Awesome. Okay, say for instance I had the sulfur ion, so it's sulfur 2 minus.
Okay.
What does that mean then? Okay, let's just compare that. I'm just going to copy this and paste it next to it. So let's just move them next to one another so you can see the difference. So on the left hand side I have sulfur atom and then I have sulfur 2 minus. What does that mean? There's 2 electrons added. So look here, I have to have 2 more electrons there.
Okay.
Does that make sense?
Yes.
Screenshot that. We are finished for today. I want you to work next week. You must finish your task work up to here in your textbook, and then we'll do questions on this, and then we'll do chemical bonding, because we're going to up the pace a bit. All right.
Okay.
Keep well.
Thank you, sir.